How you doing? My name's Bob Lee. I'm an applications engineer here at RF Venue, and I'm here to walk you through some things, some pointers about wireless for your festivals in Europe. And I know it's afternoon there; it's morning for us, so uh, things are still a little bit early. But here we go. So, so you might be wondering, who is RF Venue? Well, we make wireless mics and in-ear monitors work and sound better. This is an assortment of some of our products. We have antennas, RF systems, RF spectrum tools, and stuff like that for making things work better. We're located in the U.S. On the in the Northeast, not too far outside of Boston, and we've been around for a while, and we have more than 20,000 uh, installs around the world. So, what do we need to achieve at summer festivals? Well, we want our mics and inner monitors to work without dropouts. That makes for a happy crowd and happy sound engineers as well. So, what's unique about summer festivals? Okay, first you've got multiple stages. Typically, you have multiple acts. Sometimes you have really long distances that you have to cover with RF, and you often have a crowded RF environment with security, merchants, and all kinds of stuff going on. Of course, there's weather. We RF venue can't really help you too much about the weather, but we can give you some advice on what to do. So, what do? Well, for multiple stages, you would use a diversity pair of directional antennas on each stage, and you have to coordinate frequencies among multiple acts. Sometimes, excuse me, acts coming in bring their own wireless. You have to plan for that also. You have to plan their frequencies um, along with what else is going on in the festival. Long distances, okay, you have to use quality coax cables, and sometimes some distances are just too long for practical use with coax cables. Crowded RF environments, you have to scan your RF environment, and weather will just secure your gear and protect it from the elements. There's no real technical solution to that. What can go wrong? Well, the audience can't hear the artist. The musicians maybe can't hear themselves. Or you get RF hits, noise, and audio drops. These are classic symptoms of dropouts in RF. Now, where do things go wrong? Well, on the upper side, we have um, a wireless mic and a receiving system. What goes wrong is in the RF link. And on the IEM receiver, somewhere between the transmitters and the receiving antenna. Those are where things go wrong. And that's our domain at RF Venue. This is what we make things to handle these problems. So what we want to do with wireless audio is we want to achieve what's called capture effect. Okay, that's what happens in the receiver when the signal is at least above about 20 dB or higher above the ambient noise floor. Now, the ambient RF noise floor is just all the RF noise that's in the UHF spectrum that we use. And so in this diagram here, this little slice of spectrum, we have four wireless mic signals. Two of them are good. Look at that. They're well above that 20 dB threshold. Those are going to work fine. Now, this third one might look fine at first glance, but you can see down here, there's something else going on that frequency, on or near that frequency. So you're going to get interference on that uh, frequency. That's a mic that needs, you need to find a different frequency for. And then this fourth one, that's really in trouble because that's, you know, packed into a digital TV station. and we share the spectrum with digital TV stations, broadcast stations. So we can't use their frequencies. It's illegal. They're licensed users, and that's another frequency that would have to be moved. But once you get capture effect, and that's a phenomenon in FM receivers because we use FM for wireless audio, where the receiver, because the signal is bouncing around in frequency because of the modulation, it can't lock onto a single frequency. It's got to lock onto a signal that's jumping all over the place. So having this capture effect means that there is not a competing signal, competing noise to pull it off of locking onto that signal. Okay. So how do we achieve capture effect? We have to reduce the noise floor. So scan your RF environment and minimize the risk of intermodulation distortion. We'll be getting into how to do that a little bit later. Optimize your antennas. Okay, we're going to talk about polarization crossfade, how to minimize the number of antennas, about using directional antennas, and using quality coax cables. Okay, so we we're going to look at scanning the RF environment right now. This is a scan of the RF. Just happens to be a scan of the RF at my home uh, in Connecticut. Um, Pretty quiet. I can't even pick up any TV station, but you can see there's a little bit remnant of a TV station. This was done with our RF Explorer Pro, which is a tablet-sized spectrum analyzer and RF multi-tool. So it's got well, this is a real. The white line is a real-time analyzer, and the waterfall is below. The waterfall display is good at finding signals that are persistent, but might be kind of buried in the white line bouncing up and down. Okay, so with this and with many other types of scan tools, you can save your scan data to CSV file, which is a type of spreadsheet format. Okay, so you can use the CSV file with our wireless system builder, which is free and available on our website. Shure has wireless workbench. There's also Soundbase, and there are various other frequency coordination and calculation tools that you can use. And they all pretty much use the same CSV file format. And they will help you find frequencies to use that are not being interfered with by other signals. And you want a good, quiet environment for your wireless audio signals. And these tools will also calculate for compatible frequencies. And that's important because we're going to talk about intermodulation later and how that can raise the noise floor if you don't properly calculate your frequencies. Okay. So let's get into intermodulation. What is IMD? That's intermodulation distortion. Well, intermodulation only happens with multiple signals. It doesn't happen with a single signal. If you have two signals, well, you can get intermodulation, but the products um, that are produced from that are pretty minimal and they're easy to deal with. It's when you get three or more wireless audio signals in the same UHF spectrum. That's when intermodulation can start becoming a problem. Okay, it only happens in nonlinear circuits. It's kind of a myth that intermodulation happens in the air, in free space. It doesn't happen in antennas. It doesn't happen in coax cables, only in nonlinear active circuits. Or, if there was a passive circuit that for some reason had a diode in it, that would be nonlinear, but that's not a common occurrence. Only in nonlinear circuits. So any active circuitry that we use in the receiving side, or the transmitting side for in-ear monitor systems has to be really highly linear. Okay, so intermodulation produces signal artifacts, and they're not harmonics; they're artifacts. They're not harmonically related to the original signals. They're the sums and differences of the original signals. So you get some weird combinations of product frequencies that uh, that happen when signals intermodulate. And and like it says here, are intermodulation artifacts that lie within our UHF spectrum that can raise the noise floor. Now we're going to look at how signals coexist in a linear circuit or in the air. Okay, this display shows 9 separate wireless mic signals. Probably could be in-ear monitor signals too, but 9 separate ones. They vary in level because maybe the people with the wireless mics are different distances from the receiving antenna. But in an antenna, in the air, in perfectly linear circuitry, they coexist perfectly well. There's 9 separate frequencies. They're easy to separate out in the receivers. But what happens if we overload an active circuit, like maybe an inline amplifier or an active antenna or a distro or something like that? Somehow we put in too much signal and we end up clipping this composite waveform. Now those 9 frequencies are not coexisting. They're intermodulating with each other. They're affecting each other. And that produces products that really raise the noise spectrum, the noise floor. Now that power spectrum before that had only 9 frequencies in it, now have a whole bunch of them, and they've actually overwhelmed some of those lower signals. So that's the importance of guarding against intermodulation. So we have what we call I recommend what we call a three-pronged defense against IMD. Okay, so there's frequency coordination, as I mentioned before, and even our RF Explorer Pro spectrum analyzer can do frequency coordination calculations. Bandpass filtering, we're going to talk about that pretty quickly. That keeps out unwanted signals. So if you can get a bandpass filter, a pair of them, and a filter that will pass only the frequencies that you want and keep out TV stations or 5G phones, and from the lower end of the spectrum, we get noise from video walls and stuff like that. We have video walls increasingly at festivals and stuff, things like that. If we can filter out all that noise, that will help lower the noise floor for our receivers. Okay, we also want to minimize the active circuitry between the receiving antennas and the receiver inputs. So don't use active antennas or inline amps unless it's absolutely necessary. That's an absolute last resort. If you use RF devices like distros with high dynamic range, you'll have a lot more flexibility than if you use just, poorer quality RF devices. Okay. So I mentioned bandpass filtering. We have 6 different models. If your wireless mic frequencies fall within one of these pass bands here, that's the one to use. You use 2 of them, use them in pairs at the inputs to your distro. That will eliminate a lot of problems. Nobody ever regrets bandpass filtering their wireless mic receiving systems. Okay, more on reducing the noise floor and minimizing the risk of IMD. Okay, I mentioned minimize the active circuitry between the receiving antenna and receiver inputs. Like I said, don't use active antennas or inline amplifiers unless they're absolutely necessary. Use suitable distro products, preferably with high dynamic range circuitry. And our venue, we kind of specialize in making in distro products, among other things. But we do have products with high dynamic range. Okay. So now that we've looked at minimizing the noise floor, now let's look at how to optimize your antennas. You want to optimize the RF transmission because that's what's carrying the signal. Okay. So we're going to look first at the concept of antenna polarization, the problem of crossfade. Now, to demonstrate how crossfade works in with antenna polarization, we have this little demo video here. A little makeshift antenna, which is just two pieces of wire with a little grain of wheat uh, light light bulb in the middle, and we're going to excite that antenna with this handheld, you know, this handheld transceiver. So notice that there's enough RF energy coupled into those wires to light that bulb. But if you turn the transmitting antenna 90 degrees, it's gone. And that's the problem with linear polarized antennas is they're great when the polarization of the transmitted signal is in line with the antenna, but when the polarization of that signal approaches 70, 80, 90 degrees off angle, the pickup drops tremendously. So, and that comes into play with our wireless mics too. And so if you look at one of our products here, the Diversity Fin, that's a diversity pair antenna all in one unit. So it's a co-located pair of antennas, a vertical paddle for the vertical component, and a dipole for the horizontal polarized signal. So in this sort of situation, if the transmitting antenna is vertical, it's going to pick up well on the vertical paddle. The person holds the mic at a 45-degree angle. You're going to pick up on both the vertical antenna and the horizontal paddle. I mean, horizontal dipole. And if he turns the mic completely sideways, the horizontal dipole is going to pick up a good signal, and the vertical paddle is not going to be there. But that's fine because that's all we need with diversity reception. Now, you should all be using diversity reception for any kind of professional wireless mic situation because the days of using little very cheap non-diversity wireless mics, that's out of the question in for professional use, especially in like festivals where people are paying money for a good show. They want the show to go on. So if you have an antenna system that pays attention really pays attention to the issue of antenna polarization, then you'll have a show that goes on. You don't get a showstopper. That's the problem with using, say, two vertical paddles. Okay, it's diversity, which is good, but you're also not taking into account that you could get a dropout on both antennas at the same time because they're only looking at a single polarization. Okay. Now we can also try circular polarization, and polarization, of course, is caused by determined by the transmitting antenna, the electrical field and the magnetic field of the radio signal. That's what a radio signal is, both an electric field and a magnetic field. The electric field is determined by the position of the transmitting antenna. So this could be like the little whip antenna on a body pack mic, or it could be the little internal whip antenna in a handheld mic. Um, or this could be also if you look at the other way, from an ear monitor transmitting antenna. Okay, so if the receiving antenna is in line, with the electrical field, then you'll get good transmission. If it goes off axis, off angle, like we saw with that light bulb, the reception is going to drop off. So this is why um, we can sometimes have dropouts on an antenna, on a like a paddle antenna or a whip antenna, even though there's a direct line of sight with the transmitter. This is what happens, that polarization of the signal gets off axis from the receiving antenna, and then we get a dropout. Now, one thing we can do, this is especially effective with in-ear monitor transmitters, is use a circularly polarized signal. And this is the CP beam antenna. It's got a directional antenna. It's got a good forward gain, about 10 dB or so. And the signal from it, you use as a transmitting antenna for in-ear monitors, it's circular polarized. So that means it's putting out a signal at all angles of polarization. It's just that there's a phase shift among all the different angles, but you don't have to worry about that. The important thing is that regardless of the position of the receiving antenna, which in this case is an in-ear monitor body pack, the little whip antenna, which we can't control how a person wears that or what position they're going to be in, that whip antenna is going to pick up a good signal no matter what. Okay? So things to know about circular polarization, that they're ideal for in-ear monitor transmitting antennas. Okay? And for wireless mics, they you can use those in spatial diversity. In other words, two antennas set up. It's a great alternative to polarization diversity, like the diversity fin. And those CP beam antennas have a pretty long pickup pattern, so they can be good for a pretty long range if you need to. And be sure to minimize the number of antennas. The ideal number of antennas for any stage is just two. That would be one diversity pair. Okay, so it could be the diversity fin, one of those, because that's two antennas in one, or maybe two CP beam antennas. Those are great. You just use one diversity pair because you don't want an antenna farm. You sometimes see this in, like, nightclubs and restaurants or whatever, where they have a stack of receivers and they just take the whip antennas out of the box and put them on the back. Well, that's creating a great big noise field around those antennas because antennas interfere with each other. So just a single diversity pair for a stage, and one in-ear monitor transmitting antenna per stage if you can. Use distros to split the A and B antenna feeds for the wireless mic, to split those out into the receivers. Use combiners to combine your in-ear monitor transmitters into one antenna. Okay, so another tip: use directional antennas. That's ideal for helping to reduce the noise floor also, because they're more sensitive in a particular direction and less sensitive to other directions. So aim the antennas where you want to pick up the signal, or for transmitting antennas, aim them at where the people with the in-ear monitor receivers are going to be. Okay, so place and aim them suitably. We're going to get into antenna placement and aiming a little bit later. So along the strategy of minimizing the number of receiving antennas, so you use a diversity pair. It could be one unit, like the diversity fin, or it could be two, like the CP beams, and run those into a distro. If you need more outputs than one distro gives you, you can cascade them another level. And in this case, with our distro 4 product, which has actually 5 outputs, you can cascade those into 5 more distro 4s and feed as many as 25 diversity wireless mic receivers. So also minimize the number of transmitting antennas. Use just one antenna and a suitable combiner. This is our Combine 8 product that joins up to 8 intermonitor transmitters into one antenna. The maximum input per input, that maximum input power per input is 60 milliwatts or plus 18 dBm. But it's a good idea to, just back off a little bit on your transmitter power and use the gain of the antenna, like the gain of the CP beam antenna to compensate for that. It's got 10 dB of gain, so and gain in an antenna is just it just means that most of the power that it's radiating is focused in the direction that it's aiming in. Okay, it doesn't mean that there's active circuitry that's boosting the signal. It's just taking the signal that might normally go all the way around and just focusing it in a particular direction. Okay, so you have a stage in a front of house position. Let's plan some antennas. Okay, so here's a main stage, audience, front of house. Uh, Put a CP beam over on the side, over at monitor world, so the monitor mixer can be in charge of that. Aim it across the stage. That's a good line of sight, circular polarized coverage for your inner monitors, and that's a really great solution for in-ear monitors because it's you get a good signal coverage. It's directional. It's not going everywhere in the area. It's going over the stage and it's circular polarized. So the musicians, singers, and everybody are going to pick up that signal no matter what their position is. Okay, what do we do for mics? Well, let's put a diversity fin, D-fin, over on the side also. Okay, so now we have diversity antenna coverage, and you could put it out at front of house also, but in this case, it might be really long distance from the front of house to the main stage. Especially if your RF environment is kind of crowded, it's a good idea to put the antenna kind of close to the where the action is. And this note on the bottom is important. Never point the inner monitor at the mic antennas, okay? So you wouldn't put the CP beam here and the D-fin over here because you would just be beaming UHF spectrum energy into the D-fin, and that's going to crowd that's going to crowd the signals that you're trying to pick up with the D-fin, okay? So what if it's a really long distance and it's kind of impractical for regular coax cables? Well, you can go with lower loss coax cables, like instead of RG8, maybe going with LMR 400, but that's a lot more expensive and the cable is kind of bigger and clunkier and harder to work with. Or you can use optical fiber, and we have the Optics 3, which can go as you can run optical fiber as far as 5 kilometers even. So if you're more than if you have a coax cable run of more than 70 millimeters, start considering something other than the common RG8. You need something that's lower loss. And optical fiber is a absolutely lossless way of bringing RF. It just takes the RF coming in and converts it into light, modulates that onto light, that's carried over optical fiber, and the receiver takes that modulated light and brings it back, demodulates it into the original RF. So for diversity, you would need two of these, and it's a really effective situation. Not only for festivals, but for any really large outdoor event. It's used in air shows, marathons, um, you know, race, um, auto and horse race events and stuff like that. Anytime where you have to have the receiving antenna is maybe a really long distance from the receiver rack. If you have more than one stage, um, in this case, we have an auxiliary stage off to the side of the main stage, shorter distance to the stage, and the monitors are being mixed from the main console. So here we got the DFIN and the CP beam, right at the front of house. That they're aimed at the stage. And also, you'll notice that we're we're taking care to not aim antennas at the other stage as well. So in this sort of arrangement, you wouldn't want to have these antennas maybe over on the other side of the stage. This is a good arrangement here. They're not, these antennas aren't pointing at the main stage. The main stage antennas aren't pointing at the auxiliary stage. Okay. So use quality coax cables, 100% shielding. That's an important thing because the whole idea behind coax cables is that there's no loop area that can pick up, RF interference. You have one conductor inside of another. It's not possible to make two conductors occupy the same space, but we can kind of mimic that with a coax by having one conductor inside of another. And when there are gaps in the shielding, well, that concept of one conductor inside of the other, yeah, that kind of diminishes a bit, and then that lets in RF noise. Okay. Like I mentioned, consider using lower loss cables for really long runs, or use optical fiber. Okay. So that's it with optimizing antennas. So now to summarize, understand summer festivals can have some unique challenges. You understand what can go wrong and understand what you can do about it and how RF venue can help. Okay. So that's it. Any questions?
We didn't get any questions during your presentation because you explained things so thoroughly, Bob, that I don't think there are any. So that's a great thing. Of course, if there are any, please enter them now. We'll be happy to call them out. We did get some pre-submitted questions, so let me go ahead and start that so you can answer those. So this is my favorite question for our company. Why use RF venue antennas and not others?
Okay, our antennas, um, we design our antennas to account for polarization. Okay, panel antennas are great, but they only pick up a single polarization. You know, and they're fine for about 300 degrees, 330 degrees or so of all the possible polarization angles. When you get close to 90 degrees, like 70, 80, 90 degrees, the the pickup drops off. So we decided, when we discovered that this is a real problem that often goes unaddressed, this is why we came out with antennas like the diversity fin, which is kind of our flagship product, the CP beam, which is circular polarized, uh, an antenna that works great for transmitting a circular polarization. It's also great at receiving because it picks up any angle of polarization from the transmitting antenna. So that's why our antennas um, just work a lot better than you might be used to. Okay.
Great. We just got a question here. This is a good one. Can we have an example of inline amps when talking about lowering noise floor and best practices if in the need of using one?
Okay, like I said, don't use inline amps unless it's really, really absolutely necessary. Um, because they tend to, well, they can solve problems, but they tend to cause other problems that might not be present all the time, but they pop up now and then. When you overdrive an inline amplifier or any active circuit that's in the receiving end, you get intermodulation, and intermodulation noise when it impacts the capture effect on the receiver. That sounds awful. I mean, it can cause like a distortion because you have one signal that's intermodulating with these the signal that we're trying to receive, and you pick up some really harsh, weird sounding noise in the receiver, and the receiver can't necessarily distinguish between that noise and the signal that is trying to detect. Okay, so um, I would avoid using inline amplifiers as much as possible. And if you do have to use them, locate them away from the antenna so that you get some, you use it to overcome loss in the coax cables rather than just have a big signal boost up front. Okay, so use it away from the antennas so that you're less likely to overdrive the inline amplifier, and use them sparingly. If you can dial in the amount of gain, start with the lowest gain possible, and and see how that works, and then turn it up only if necessary.
Great. All right,
Okay.
Bob. Here's a good one for you. How to solve an RF problem like interference a few minutes before the show?
Oh, that can be a challenge. Yeah, this is why you really need to, uh, if you can, scout out your location well in advance and see what your RF environment is as far in advance as you can. But there are also things that will pop up on the day of the show, and that's often with security and merchant communications and stuff like that. If you can become a good friend with the festival producer, so that you make it clear to the producer that you should have really good priority on RF selection, and that will help it because the show's got to go on, and if it's a good show, you'll have a happy audience and you'll have a happy festival producer. Um, what happens in the last minute can sometimes be really difficult to deal with. If you have spare channels of wireless, sometimes you might have to just go into your board and change the channel assignment to a different receiver, and use a different frequency. How well how much um, how much redundancy do you have in your system that can help you with overcoming problems? But each situation is different, so sometimes you just have to be able to improvise quickly.
Excellent, excellent. This is a really good question coming up, and it's very common in the audio industry on nearly everything. But I don't think it's well understood in RF. Perhaps you can demystify this, Bob. Why
Sure.
is digital wireless system better than analog wireless system?
Uh, well, they have. Well, the thing with digital is that if the digital stream is intact, you're going to get a noise-free, distortion-free audio transmission. An analog transmission can be influenced by interference and stuff like that. Now, it takes a little bit more signal headroom to transmit a digital signal sometimes, but if you can do digital, then there's there's often a really great benefit. Now, one one thing with digital, sometimes you get latency that might be noticeable, um, because the process of converting a an analog, you know, wave from your voice or an instrument or something like that into digital, it takes a little bit of time, a few milliseconds possibly, and change that into a digital packet to be, a series of digital packets to be transmitted. So sometimes people complain about, singers might complain about, they're hearing their voice just a little bit behind what they're actually singing, you know. So I think digital technology has gotten a lot better in recent years. I can remember when even like sending digital audio over like Ethernet cable and stuff like that. You often had like about milliseconds of latency. They've gotten that down to less than 1 millisecond in a lot of cases now. So that problem goes away. So digital is a lot better than it used to be. I remember the first digital systems back in the 90s, and they were an interesting step forward. They were good ideas, but sometimes they had problems. But I think you'll find that the digital systems now are really pretty solid.
Great, Bob. And another question just came in on the subject of minimizing antennas. For, say, a 16-channel IEM system, do you feel it's better practice to use two 8-channel antenna combiners with one helical antenna, or keep both combiners independent with their own helical antenna physically spaced apart? Does combining combiners raise the noise floor at a higher cost than using multiple antennas?
If you have two combiners and you have a good passive combiner, you you don't get a raise in the noise floor. If there's good isolation between the inputs, so that one's not, excuse me, feeding into the output of the other and vice versa, you can go ahead and feed a single antenna. The antenna doesn't care how many channels there are. It's just a passive thing. It's just radiating that signal, those signals, all together. And that can, well, the antenna uh, just doesn't care. There's a concept in physics called superposition. You can have a whole bunch of different signals perfectly coexisting on that antenna, and they're being transmitted out over the stage. So if you can get by with just one antenna, that's a good way to go.
Excellent, Bob. If there's no further questions, I believe we've run the course here. Last chance, anyone? We've answered all the questions you've submitted. Thank you for that. Like I said, I'm going to go ahead and send you a feedback survey. Please let us know how we did. We'll be posting this recording onto our webinar page as well. So feel free to forward to anyone who wanted to be here but couldn't. And again, thank you for your time. Bob, thank you for your presentation. That was amazing. Feel free to send us any questions. You can reach the team at info@rfnu.com. We're all on that email address, so we look at it daily, and we're happy to answer any technical questions, product-related questions, or any general RF questions that you may have. So thank you for your time, and we look forward to seeing you on the next one. Cheers, guys. Take care.